Hi everybody, so here's our first content video on the oxidation reduction reaction and electrochemistry in general. The place where we have to start is a little bit dry. We have to get through some kind of basic concepts, and they're not all that exciting. And you can actually find them in sections 4.9 and 4.10 of your textbooks. Electrochemistry is actually chapter 17, but we have to go back to a couple of sections in chapter 4 to be able to set up the content for chapter 17. So in this video, I'm going to go through a couple of things, some basic language that's associated with oxidation reduction, and the idea of assigning oxidation states. All right, so let's get into it. Electrochemistry is based on the oxidation reduction reaction, which is also known as a redox reaction. And what a redox reaction involves is it involves the transfer of electrons. So something is going to be the electron source, and something is going to be the electron sink. So we have a donor and we have an acceptor. Here's the lingo. The donor is said to be oxidized. When something loses electron density, it is said to be oxidized. Now this is a little bit of a historical term because when chemists were first exploring this kind of chemistry, they noticed that when materials tended to lose electrons, they also tended to gain mass in the form of oxygen. So the term oxidation has kind of stuck around. The acceptor, the material that is receiving the electron density, is said to be reduced, and you can think about this in terms of its positive charge, right? Its positive charge would be reduced if something accepted electrons. Now, we also have a little more language here. The thing that is the donor, that is being oxidized, is a reducing agent. It can go ahead and reduce the acceptor, which is getting reduced, and it itself can be referred to as an oxidizing agent because it is extracting the electron density from the donor. So we're not going to use the terms donor and acceptor really very much. We're going to refer to things being oxidized and reduced, or to things acting as a reducing agent or acting as an oxidizing agent. So get comfortable with the lingo. All right, to help you understand oxidation reduction a little bit, we have a couple of these sort of handy-dandy memory devices. Oil rig and Leo says GR. So oxidation involves the loss of electrons, reduction involves the gain of electrons, and Leo says GR. Loss of electrons is oxidation, gain of electrons is reduction. So use one of these mnemonic devices to help you remember what oxidation means and what reduction means. We're going to have a couple of other handy-dandy little memory devices in this unit that will help you keep track of what's going on. Now let's get to a little bit more specific content. The oxidation reduction reaction is based on electrons coming and going. So we need a way to assign where the electrons currently are. And to assign electrons to different atoms in a molecule, we're going to use the concept of oxidation states. Oxidation states are very similar to formal charge that you learned about when you did Lewis dot structures as sophomores. So I'm going to go through some general rules, and then we'll get into some more specific rules as we go along here. So the first general rule: the electrons found in a covalent bond between identical atoms, those electrons get split evenly. So imagine the electrons in a carbon-carbon bond. What ends up happening is we treat one of those electrons is going to the carbon on the left, and one of those electrons is going to the carbon on the right. How about we had covalent bonds between different atoms? So imagine a CF bond. Here, the electrons are going to go or be considered to be part of the sphere entirely of the more electronegative atom. So those two electrons in the CF bond, none of them go to the carbon, but both of them would be considered to be part of the fluorine's sphere. Okay, so this is how we're going to distribute electrons as we try to figure out this idea of assigning oxidation states. Some more rules, and now we're going to start to get a little bit more specific. For ionic compounds, the oxidation states are equal to the ionic charge. So if you have the compound sodium chloride, then the sodium has a +1 oxidation state and the chloride has a -1 oxidation state. You'll see that I'm going to do this technique where I write the oxidation state above the atom. That's kind of the convention that you'll see out there, and we're going to follow that. So as I put these things that look like charges above the atoms, what we're really doing is we're assigning them oxidation states. And it's important to keep in mind that oxidation states are not charges. Charges are real. Charges actually exist in the physical world. Oxidation states are a formalism. They're a way of doing electron bookkeeping. So don't confuse an oxidation state with something that's real. It's just a handy-dandy device that we use to keep track of electron density. All right, rule number 4, if you have an element, or if you have an atom in its elemental form, then its oxidation state is going to be 0. So imagine we have elemental carbon. Its oxidation state is 0. Imagine we have nitrogen, okay? Then nitrogen kind of looks like this when you draw its Lewis dot structure. Both nitrogens have an oxidation state of 0. So when you're talking about atoms in their elemental state, then we are talking about materials that have an oxidation state of 0. Next, the oxidation state for monatomic ions is the same as its charge. So if you have sodium ions, say, floating around in solution, right, it has a +1 charge, then it's also going to have a +1 oxidation state. Very similar to rule number 3. Fluorine. Now we're going to start to get even more specific and start to talk about specific atoms. Fluorine will always have, when it's in a compound, the oxidation state of -1. So if we think about, say, CF4, the fluorines in CF4, each of them have an oxidation state of -1. The only exception to this rule would be the molecule F2, which is going to go back to one of our previous rules where it's going to have an oxidation state of 0. So if you see fluorine in a molecule bound to other atoms, the oxidation state of fluorine is going to be -1. And that's because fluorine, as you know, is the most electronegative element, and so it's always going to take the electron density and end up with a -1 oxidation state. All right, oxygen. There's a couple of specific rules for oxygen. Most of the time you see oxygen in a compound, it's going to have the oxidation state of -2, right? It's going to have a -2 oxidation state. The only exception there is when you see, two exceptions actually, is when you see oxygen as a peroxide or oxygen bound up with fluorine. So here are the 3 examples. Here's water. Water is going to have oxygen with an oxidation state of -2. Here's a peroxide. And you know it's a peroxide because it's X2O2. Anytime you see the X2O2 format, that oxygen is acting as a peroxide polyatomic anion, and each oxygen will have a -1 oxidation state. And then lastly, the specific molecule OF2. Because each fluorine has to have a -1 oxidation state, then the oxygen ends up having a +2 oxidation state. You're going to see how we can add and combine oxidation states to find out the oxidation states of unknown atoms in a minute. So we'll do a more detailed example in just a second. Let's talk about hydrogen. Hydrogen, when it's bound up with nonmetals, that hydrogen is going to be less electronegative than the nonmetal. So it's going to lose electron density to the nonmetal and have a +1 oxidation state. However, if the hydrogen is bound up with a metal, hydrogen is more electronegative than metals, and so it's going to take electron density and have an oxidation state of -1. So first example here is ammonia. Nitrogen is a nonmetal, so the hydrogen has an oxidation state of +1. Lithium hydride. Lithium is a metal, so it will give electron density to the hydrogen, and so hydrogen has a -1 oxidation state. And then lastly, rule number 9. The sums of the oxidation states have to add up to the overall charge of the material. So if we're talking about neutral compounds, then the individual atomic oxidation states have to add up to 0. If we're talking about a charged species, then the individual oxidation states have to add up to the charge of the material. Let's go ahead and take a look at some examples. Here's carbon dioxide. We don't have a rule for carbon, but we do have a rule for oxygen. Okay, Okay, the oxygen here is going to have an oxidation state of -2. There are two oxygens, each with an oxidation state of -2. So the total charge from oxygen, and I put charge in quotes there, is -4. Carbon dioxide taken together is a neutral molecule, so the sums of the oxidation states have to add up to 0, which means that carbon has to provide a total of +4, and there's only one carbon atom, so its individual oxidation state is +4. So the oxidation states are the numbers I'm circling in red there. The numbers that I'm going to, let's see, circle in, let's say pink here, these are the total charges or total values of all the oxidation states combined. But when I report the individual oxidation states, it's the numbers in red that I'm going to care about. Okay, methane, CH4. Well, we have a rule for hydrogen. Hydrogen here is bound to a non-metal carbon, so it's going to have the oxidation state of +1. I have 4 hydrogens for a total of +4 altogether. Methane is a neutral compound, so the carbon has to bring to the party -4. There's one carbon, so it itself brings -4 to the party. So there again are my oxidation states. Take a look at what happened between these two examples for carbon. Carbon had a +4 oxidation state in carbon dioxide and a -4 oxidation state in methane. And carbon is very precocious when it comes to its oxidation state. It actually can have an oxidation state of +4, +3, +2, +1, 0, -1, -2, -3, -4. That's why we don't have a rule for carbon, because it's kind of all over the map. All right, and lastly, we have the compound potassium dichromate. Well, let's see if we can use some rules here. Potassium dichromate, these are ions, so I know that I'm going to have some charged species here. For example, the potassium is going to have a +1 oxidation state because potassium is a +1 ion. I have 2 potassiums, so that's going to bring a total of +2 to the party. That's a 2 there. Oxygen has an oxidation state of -2. I have 7 oxygens, and so they're all together bringing -14 to the party. Potassium dichromate taken as an entire unit should be neutral, so all of that has to add up to 0, which means then the chromium is bringing +12 to the party. I have 2 chromiums, so each individually is bringing +6. So my oxidation states there are +1 for potassium, +6 for chromium, -2 for oxygen. Let's take a look at one more example. How about the polyatomic ion of nitrate, so that we can look at a charged species? The oxygen brings -2 to the party. There's 3 of them for a total of -6. Nitrate has a -1 charge on it, so the nitrogen has to bring +5 to the party. There's 1 nitrogen, so it itself brings +5. So my oxidation states for the atoms in nitrate are +5 for nitrogen and -2 for the oxygen. All right? So assigning oxidation states is fundamental to doing redox or oxidation reduction chemistry. So we should practice this more and more. This has to kind of become automatic. Take one more question here and take a look at some of the language. When we take a look at this oxidation reduction reaction, let's see if we can answer some questions here. Which species is being oxidized? Well, in order to figure this out, we should go ahead and assign some oxidation states. All right, the hydrogen here is going to be +1, which means the carbon's going to be -4. Oxygen here is 0. Oxygen here is -2, which means that the carbon is going to be +4. The oxygen in water is -2. The hydrogen in water is +1. So there are my oxidation states. So now, which species is oxidized? Well, take a look here. The carbon goes from -4 to +4, okay? So it looks like it is losing electron density. So the species that's being oxidized is the methane. Specifically, it's the carbon of methane that ultimately is oxidized, but it's easy enough to say in this reaction that methane is oxidized. All right, what's being reduced? The oxygen's going from 0 to -2 in either the carbon dioxide or the water. So it turns out that it is the oxygen that is getting reduced. Therefore, which species is the oxidizing agent? Well, oxygen is the thing that's grabbing the electrons away from methane, so it is the oxidizing agent, and methane is the material that is bringing electron density towards the oxygen, so therefore the methane is the reducing agent. So that is a little bit about the language of redox chemistry and the process of assigning oxidation states. Assigning oxidation states has to be automatic and it has to be quick, because for the next thing we're going to talk about balancing redox reactions. Finding oxidation states is often the first thing you have to do, and you want to be able to do it efficiently and correctly. See you next time.